This is literally everything to know about artificial intelligence, at a slow pace perfect for sleep and relaxation. Its long history, controversial impact on the public, and the advanced algorithms behind models like ChatGPT and Claude will all be covered in this one video. I hope you find this interesting. There's a small mechanical duck in a museum storage room in France that no longer works, and which nobody is entirely sure they know how to fix. In 1739, when it was new, the duck could do something that made grown men write letters to each other in astonishment. It would stretch its neck. It would flap its wings, feather by individual feather, over 400 of them, each one articulated. It would eat grain from a person's hand. And a little while later, through a mechanism its inventor never fully explained to anyone, it would appear to digest that grain and excrete something that looked convincingly like waste. People called it the digesting duck. Its inventor, a Frenchman named Jacques de Vaucanson, never claimed it was alive. He was a maker of clever machines, not a magician, and he understood exactly which gears turned which rods to produce which motion. But the people who watched it eat didn't entirely care about the gears. Something in them wanted to ask a harder question, one that machines hadn't really forced anyone to ask before. If a thing behaves like a living process closely enough, does it matter that you know it's made of brass? That question is older than computers, older than electricity, older than the word robot, which wouldn't even be invented for another 200 years. And it's the question sitting quietly underneath everything we're going to talk about tonight. Not can a machine think, exactly. We'll get to that specific phrasing later, because someone eventually asked it directly, and the way he asked it turned out to matter a great deal. For now, something gentler, something closer to what those 18th century observers were really wrestling with as they watched a copper duck swallow oats. What is it about a process, mechanical, electrical, mathematical, that lets us look at it and see something like a mind? We're going to spend the next couple of hours following that question as it moves through history. It travels through looms and calculating engines, through a Cambridge mathematician cracking codes in a country house during a war, through a summer workshop at a college in New Hampshire, where a group of researchers gave a new field its name almost as an afterthought, through decades of enthusiasm and disappointment and quiet, unglamorous progress, and into rooms full of computers doing something that still, honestly, nobody fully understands. Learning, you don't need to remember any of the names. You don't need to hold on to any of the dates. Let them wash past you if they want to. What matters is the shape of the story, and the shape of the story is this: a very long series of people trying to build a version of thought out of things that clearly aren't alive, and slowly, unevenly, sometimes by accident, getting closer than they had any right to. Long before anyone tried to build a thinking machine, people were building machines that performed the appearance of will. Automata, they were called, and European royal courts loved them the way people today love a genuinely good magic trick. Not because they were fooled, but because they enjoyed not quite being able to explain the feeling the trick produced. There were mechanical monks that raised wooden crosses to their lips. There were brass birds that sang and turned their heads to follow a viewer around a room. There was, in Vaucanson's workshop alongside his duck, a mechanical flute player, a life-sized figure with actual lungs made of bellows, actual lips that moved to shape the airstream, fingers that pressed down on actual flute holes in something close to real time. It wasn't playing a recording. It was, in a very literal mechanical sense, playing the flute. None of these machines were intelligent, not by any definition we'd use today, and nobody who built them thought otherwise. They followed fixed sequences. Wind the spring, and the same motion happens the same way, every time forever, until the mechanism wears out. But they taught European engineering something important almost by accident. That complex, lifelike behavior didn't require magic. It required precision. It required someone willing to sit down and work out, piece by piece, exactly which small mechanical action needed to happen before which other one, so that the whole sequence, strung together, produced something that looked, from a slight distance, like a decision. That idea, that a fixed sequence of small operations could add up to something that resembled intelligent behavior, turned out to be far more important than any single duck or flute player. It just took a different kind of machine to show why. The machine that mattered most wasn't trying to imitate life at all. It was trying to weave silk. In the early 1800s, a French weaver named Joseph Marie Jacquard was trying to solve a problem that had nothing to do with mines and everything to do with looms. Weaving an intricate patterned fabric, brocade, damask, anything with a repeating design worked into the cloth itself, required a weaver to manually lift specific threads in a specific order, over and over, thousands of times, for a single piece of fabric. It was slow, it was exhausting, and it required a second person, usually a child, sitting inside the loom itself, pulling cords in the correct sequence by hand. Jacquard's solution was a string of punched cards, each one riddled with holes in a particular pattern. As the cards fed through the loom, mechanical rods would try to poke through each card. Where there was a hole, a rod would pass through and lift its thread. Where there wasn't, the rod would be blocked and the thread would stay down. String enough cards together in sequence, and you could encode an entire pattern, a whole design, however elaborate, as a physical, readable sequence of instructions. Change the cards, and the same loom would weave a completely different pattern. The machine hadn't changed. Only the instructions had. This is worth sitting with for a moment, because it's easy to let it slide past as just a clever piece of textile history. What Jacquard had actually built was something new in the world, a general-purpose machine, in a limited sense, that could be reprogrammed by feeding it different data. The loom itself was dumb. It had no opinion about what it was weaving, but the pattern of holes carried the intelligence, or at least, carried a set of decisions that had once required a thinking person to make them, one lifted thread at a time. Word of the Jacquard loom spread across Europe, and eventually in London, it reached the desk of a mathematician who was in the middle of what might be the most stubborn, most expensive, and most quietly visionary failure in the entire history of computing. His name was Charles Babbage, and he was tired of mistakes. Specifically, he was tired of the mistakes that crept into mathematical tables, the printed books of logarithms and trigonometric values that ship navigators, insurance actuaries, and engineers depended on for every serious calculation of the era. These tables were compiled by teams of human calculators, working through long chains of arithmetic by hand, and the calculators, being human, occasionally slipped. A single wrong digit could compound through a navigator's calculations, and in the worst case, run a ship onto rocks it should have cleared by miles. Babbage's first answer to this problem was a machine called the difference engine, designed to compute tables mechanically, using a clever mathematical technique that let you generate a whole sequence of values using only addition, repeated in a fixed pattern. No human judgment required, and therefore, in principle, no human error. He built a working portion of it. It was beautiful and enormous and made almost entirely of brass, and the British government funded it for years before losing patience with the endless cost overruns. But it was Babbage's second machine, the one he never finished, that actually matters to our story tonight. He called it the analytical engine, and it was not a table calculator anymore. It was something closer to what we now recognize, squinting a little, as a computer. It had a section for storing numbers, which Babbage called the store. It had a section for performing operations on those numbers, which he called the mill. And if those names sound like they belong in a textile factory rather than a computing device, that's not a coincidence, because Babbage borrowed the architecture quite directly from the Jacquard loom. His analytical engine was meant to be fed instructions on punched cards, exactly like Jacquard's fabric patterns, except instead of encoding which threads to lift, the cards would encode which arithmetic operations to perform, and in which order, and on which stored numbers. A machine that could be told what to do through cards, and would do different things depending on which cards you fed it. That is, in the most basic possible sense, the core idea of every computer that has ever run since. Babbage never got it working. The precision engineering required was simply beyond what Victorian workshops could reliably produce, and he spent decades and most of his personal fortune chasing a machine that outran the manufacturing tools of his own century. But the idea of the analytical engine attracted the attention of a young mathematician named Ada Lovelace, the daughter of the poet Lord Byron, and it's through her writing, specifically, through a set of notes she wrote to accompany a translated paper on the engine in 1843, that we get the first serious attempt to think through what a machine like this might actually be capable of, beyond arithmetic. Lovelace understood something that even Babbage hadn't fully articulated. She realized that because the analytical engine operated on symbols according to rules, rather than on quantity specifically, it wasn't limited to numbers at all. If you could represent something, anything, really, as a symbol, and define rules for how those symbols should be manipulated, the engine could in principle work with it. In one of her notes, now simply called Note G, she suggested the machine might one day be used to compose elaborate pieces of music, if the rules of musical composition could be expressed in the kind of terms the engine could act upon. That's a genuinely startling thing to have written in 1843, more than a century before anyone built a working general-purpose computer, let alone asked one to generate a melody. But Lovelace also wrote something else, something quieter and more skeptical, that would end up echoing much further into the future than anyone at the time could have guessed. She observed that the analytical engine had no pretensions to originate anything. It could only do whatever we knew how to order it to perform. It could follow analysis, she wrote, but it could not anticipate any analytical relations or truths. In other words, powerful as it might be, it wasn't creating anything new. It was only ever executing, however elaborately, the intentions of the person who wrote its instructions. That observation would later get a name of its own. People would come to call it Lady Lovelace's objection. And it would resurface, again and again, at nearly every major turning point in the history of artificial intelligence, usually right around the moment some new machine seemed to be doing something its designers hadn't explicitly told it to do. We'll meet that objection several more times tonight. Keep it somewhere in the back of your mind, loosely, the way you'd keep track of a character introduced early in a long novel who you suspect is going to matter later. She usually does. For now, though, the analytical engine remained unbuilt, a beautiful diagram of a machine that wouldn't exist for another 100 years. Babbage died in 1871, having built a fraction of his vision and none of Lovelace's speculative extensions to it. And for a long while afterward, the idea of a machine that could manipulate not just numbers but symbols, the idea that would eventually make artificial intelligence possible at all, went quiet. It didn't stay quiet in engineering, exactly. It went quiet in engineering and picked up somewhere else entirely, in the strange, abstract, seemingly impractical world of formal logic. Around the same time, Babbage was fighting with brass gears in London. A largely self-taught mathematician in Ireland named George Boole was working on a much stranger project. He wanted to know whether human reasoning, the actual process of drawing valid conclusions from premises, The kind of thing philosophers had been formalizing since Aristotle could be written down as algebra, not as a metaphor for algebra, as actual algebra with symbols and operations that you could manipulate the way you'd manipulate an equation. Boole's insight, published in 1854 in a book with the almost defiantly plain title An Investigation of the Laws of Thought, was to reduce logical statements to a system with only two possible values, true or false, which he represented as 1 and 0, combined using operations he called and, or, and not. A statement like, "It is raining and I am outside," could be represented, manipulated, and evaluated using the same kind of symbolic machinery you'd use to solve for X. This system, now called Boolean algebra, felt at the time like a beautiful curiosity. It was elegant, it was rigorous, and for about 70 years, almost nobody found a practical use for it at all. That changed in 1937, when a graduate student at MIT named Claude Shannon, working on his master's thesis, realized that Boole's true and false algebra mapped perfectly onto something very physical and very electrical: the open and closed states of switching circuits. A closed switch could represent true, an open switch could represent false, and the logical operations Boole had described almost a century earlier, and, or not, could be built directly out of arrangements of electrical relays and switches. Shannon's thesis has since been called, only slightly hyperbolically, one of the most important master's theses of the 20th century, because it quietly handed engineers the theoretical foundation for every digital circuit that would ever be built. Every processor in every computer, every phone, every server running any of the systems we'll talk about later tonight, is, underneath all its complexity, a colossal arrangement of switches performing Boolean logic, exactly as Shannon first sketched it out as a young graduate student. Boole had built a system to describe the laws of thought. Shannon discovered, generations later, that the same system happened to describe the laws of electrical switches. Thought and circuitry, it turned out, could speak the same language. But before that connection was made, logic itself was going through a much deeper crisis, one that had nothing to do with electricity and everything to do with a question that sounds almost philosophical. Can mathematics ever fully prove itself? At the start of the 20th century, a German mathematician named David Hilbert proposed an ambitious project. He wanted to place all of mathematics on a completely secure logical foundation, a fixed set of axioms and rules from which every true mathematical statement could, in principle, be derived through pure mechanical procedure, and from which no false statement could ever be derived by accident. Part of this project, which came to be called the Entscheidungsproblem, the decision problem, asked something very specific. Is there a definite method, a procedure, an algorithm, something you could in principle hand to a tireless clerk with no understanding of mathematics at all, that could look at any mathematical statement and correctly determine, in a finite number of steps, whether it was true or false? It's a question about whether truth, at least mathematical truth, can be settled by pure mechanical process. No creativity required, no insight, just a procedure followed correctly. In 1931, an Austrian logician named Kurt Gödel delivered a result that shook Hilbert's program to its foundations. Gödel proved, with total mathematical rigor, that any formal system powerful enough to describe basic arithmetic would necessarily contain true statements that could not be proven true from within that system. Not statements that were merely difficult, statements that were, provably, unprovable using the system's own rules. Mathematics, it turned out, could not fully prove itself. There would always be true things sitting just outside the reach of any fixed set of rules you used to try to capture them. It's a strange, almost vertiginous result, the kind of thing that's easy to state and hard to fully absorb, and it's fine if it takes a moment to settle. The short version is enough for our purposes. Hilbert had hoped mathematics could be reduced entirely to mechanical procedure, and Gödel showed that it couldn't be, not completely, not ever. That left Hilbert's decision problem, the Entscheidungsproblem, still technically unanswered in its original form. And it was a young Cambridge mathematician named Alan Turing who picked it up next, in 1936, and answered it in a way that ended up mattering far more to our story than the original question did. Turing's approach was almost sideways. Rather than attacking the decision problem directly, he first asked a more basic question. What precisely do we even mean when we say something is computable? What does it mean, in the most stripped-down, mechanical sense possible, for a procedure to be capable of being carried out step by step? To answer this, Turing imagined an extremely simple hypothetical device. Not a physical machine he intended to build, a thought experiment, a mathematical object. It consisted of an infinitely long strip of tape, divided into cells, each cell capable of holding a single symbol. A read-write head that could move along the tape, one cell at a time, reading whatever symbol was there, writing a new one if instructed, and moving left or right. And a small table of rules, a finite list, that told the machine what to do based on two things only: the symbol currently under the head and the machine's current internal state. That's it. That's the entire machine. No memory beyond the tape. No cleverness. No intuition. Just a head, a tape, and a small table of if this then that rules. And yet Turing showed, with startling generality, that this absurdly simple device, now called a Turing machine, could, given the right table of rules, carry out any calculation that could be described as a definite mechanical procedure at all. Anything a human mathematician could compute by following an algorithm, step by step, with no insight required beyond following the rules correctly, a Turing machine could compute too, given enough tape and enough time. It became, almost by accident of how thoroughly it captured the idea, the formal definition of what computable even means. To this day, when computer scientists want to know whether some process can be computed at all, the question they're really asking, underneath the modern language, is whether a Turing machine could do it. And using this new, precise definition of computability, Turing was able to answer Hilbert's original decision problem, and the answer was no. There is no general mechanical procedure that can look at an arbitrary mathematical statement and always correctly determine, in finite time, whether it's true. Some questions about computation simply cannot be resolved by any fixed algorithm. A result closely related to, and independently derived around the same time as, a similar proof by the American logician Alonzo Church, which is why it's often called the Church-Turing thesis today. So both Gödel and Turing, from different angles, had shown the same fundamental limitation. Formal systems have edges. Mechanical procedures have edges. There will always be truths and always be questions that sit just past what any fixed set of rules can reach. You might expect this to have been a discouraging result for anyone hoping to eventually build a thinking machine. If even pure mathematics can't be fully captured by mechanical procedure, what hope does something as messy as human thought have? But Turing, characteristically, seemed to find the opposite lesson in his own proof. In the process of showing what computation couldn't do, he had also shown, with total precision for the first time in history, what computation could do, and it was an enormous amount. A single, simple, mechanical device, manipulating nothing but symbols according to fixed rules, could in principle carry out any well-defined procedure whatsoever. And human thought, at least the parts of it that involve following steps, applying rules, working through logic, wasn't that also, in some sense, a procedure? It would be nearly 15 years, and a war, before Turing returned to that question directly and in public. When he did in 1950, he opened his paper not with a proof, but with a proposal for a game. He called it the imitation game. A human judge sits at a terminal exchanging typed messages with two hidden participants, one a human, one a machine, and tries to determine from the conversation alone which is which. If a machine could consistently fool the judge, Turing suggested, then perhaps the question, can machines think, was less important, and certainly less answerable than a more practical one. Can a machine behave convincingly, indistinguishably as though it thinks? It's a very Turing move in retrospect. Rather than trying to settle a philosophical argument about the true nature of minds, a debate that, frankly, philosophers still haven't fully settled about human minds, let alone artificial ones, he sidestepped it entirely and replaced it with something you could actually run an experiment on. You didn't need to agree on what thinking really was. You just needed to watch and see whether you could tell the difference. That test would later be given his name, and it would take a little over 60 years and a very different kind of machine than Turing had in mind before something finally managed to hold up its end of that conversation convincingly enough to matter. But between Turing's proposal and that eventual moment lies a great deal of history. Some of it happening in a quiet English country house during the war Turing had just lived through. Some of it happening in a lecture hall in New Hampshire 11 years later, where a small group of researchers would sit down for a summer, and almost as a matter of convenience, give this entire pursuit a name. That's where we'll go next. Between Turing's 1936 paper and his 1950 proposal for the imitation game, there's a gap of 14 years, and most of that gap is taken up by something Turing himself rarely spoke about afterward, because for a long time he wasn't allowed to. During the Second World War, Turing worked at Bletchley Park, a requisitioned country estate in England where a large and unusually mixed group of mathematicians, linguists, chess players, and crossword enthusiasts had been assembled to break German military codes. The codes in question were generated by a machine called Enigma, which scrambled messages using a rotating series of electrical wheels, and which the German military believed, with good reason, to be effectively unbreakable by hand. There were simply too many possible wheel settings to check one at a time within any useful window. What Turing and his colleagues built in response wasn't a thinking machine, not in the sense we've been discussing tonight. It was something narrower and, in its own way, more immediately practical. An electromechanical device called the bomb, which didn't decode messages directly so much as it rapidly eliminated impossible settings, narrowing an impossibly large search down to a small enough number that human codebreakers could finish the job. It was a machine built to make a decision. Is this the correct setting, yes or no? Over and over, at a speed no group of humans could match, freeing the humans to apply judgment only at the very end of the process, once the machine had done the exhausting work of narrowing things down. There's a quiet thread here worth noticing, because it will recur in various forms for the rest of this story. Long before anyone built a machine that could hold a conversation, or recognize a face, or generate an image, the earliest genuinely transformative use of mechanized reasoning was this: taking a search space too large for a human to explore, and using a machine to explore it anyway, tirelessly, at a scale and speed no person could sustain. Chess programs would later do this. So would systems that search for promising drug compounds, or the network of weights inside a modern neural network, adjusting itself across a landscape with more dimensions than anyone can visualize. The particular flavor of intelligence machines turned out to be best at, right from the start, was patient, exhaustive search, not inspiration, but stamina. Turing didn't get to enjoy much public credit for any of this during his own lifetime. since the work at Bletchley Park remained classified for decades after the war ended, and his own life ended early and unjustly. Convicted in 1952 under British laws criminalizing homosexuality, chemically treated, stripped of his security clearance, dead by 1954, most likely by his own hand, at 41. It would take until 2009 for a British government to formally apologize, and until 2013 for a posthumous royal pardon. It's a hard thing to sit with, and this isn't a story that needs to dwell on it, but it also shouldn't be skipped past too quickly. The man who gave the field its most foundational theoretical tool, and its first serious proposed test for machine intelligence, didn't live to see almost any of what came next. What came next started, more or less formally, 2 years after Turing's death, at Dartmouth College in Hanover, New Hampshire, in the summer of 1956. The event has since acquired a slightly mythic status, the way founding moments often do in retrospect, though at the time it was a fairly modest affair. A roughly 2-month workshop, proposed the year before in a funding request to the Rockefeller Foundation, organized by 4 researchers, John McCarthy, then a young mathematics professor at Dartmouth, Marvin Minsky, a Harvard researcher with a background that ranged from neural network theory to genuinely eclectic mathematics, Nathaniel Rochester, an engineer at IBM who had helped design one of the company's early computers, and Claude Shannon, the same Shannon whose master's thesis had connected Boolean logic to electrical circuits 2 decades earlier. The proposal for the workshop is a genuinely remarkable document to read now, mostly because of how confidently it states its central claim. It proposes that, and this is close to the original phrasing, every aspect of learning or any other feature of intelligence can in principle be so precisely described that a machine can be made to simulate it. And then it goes on to list the specific problems the group intended to make progress on that summer, as though listing chores. How to get a machine to use language, how to get a machine to form abstractions and concepts, how to get a machine to improve itself. It's worth pausing on that confidence for a moment, not to mock it, but because it set a tone that would echo through the field for the next several decades, in ways that were sometimes wonderfully productive and sometimes quite costly. These were serious researchers, not cranks, and they weren't wrong that machines could eventually do remarkable things. They were wrong, mostly, about the timeline. Nearly every technical challenge listed in that 1956 proposal did eventually get solved, or at least meaningfully addressed. Just not within the 2 months the workshop had budgeted, and in some cases not within the researchers' own lifetimes. It's in this proposal that the phrase artificial intelligence appears in print for what's generally considered the first time, coined by McCarthy specifically for this event. He later admitted the choice was partly strategic. He wanted a name distinct enough from existing fields like cybernetics, which was associated with a different research group and a somewhat different set of ideas, so that this new effort could establish its own identity. It wasn't a name chosen because it was the most accurate description available. It was chosen because it was distinctive, and because distinctive names get funding. The Dartmouth workshop itself didn't produce a working thinking machine, obviously, and attendance drifted over its 2 months, with different researchers arriving and leaving at different times rather than the whole group working continuously together as originally envisioned. But it did something arguably more important than any single technical result. It gathered, in one place, more or less the entire founding generation of a field that didn't quite have a name yet, and sent them back to their home institutions with that name freshly coined, and with each other's phone numbers. One of the attendees, a Rand Corporation researcher named Alan Newell, arrived at Dartmouth with something the other participants found remarkable, because unlike most of what was being discussed in the abstract that summer, It already existed and already worked, at least on a small scale. Newell, along with his Rand colleague Herbert Simon and a programmer named Cliff Shaw, had built a program called the Logic Theorist, and it's where we'll pick up next, because it represents something the field badly needed after a summer of ambitious proposals. Actual, demonstrable proof that a machine could do something that looked, unmistakably, like reasoning. The logic theorist was built to do one specific thing: prove mathematical theorems from Whitehead and Russell's Principia Mathematica, the same monumental, notoriously dense work of formal logic that Gödel's incompleteness proof had, in a sense, already destabilized 25 years earlier. Newell, Simon, and Shaw weren't trying to make a general philosophical statement about the nature of mind. They were trying to see whether a machine could take a set of logical axioms and a target statement and find a valid sequence of steps connecting one to the other. A proof, in other words, built the way a human mathematician builds one, through a search among many possible next steps, most of which lead nowhere. And it worked. The logic theorist successfully proved dozens of theorems from Principia Mathematica, and in at least one case, found a proof for a particular theorem that was actually more elegant than the one Whitehead and Russell had originally published, shorter, cleaner, using fewer intermediate steps. Simon reportedly wrote to the original authors to let them know their machine had improved on their work, which is a wonderful, slightly cheeky footnote to have in the historical record. What made the logic theorist important wasn't really the theorem proving itself, though. It was the method underneath it, which Newell and Simon called heuristic search. Rather than trying every possible sequence of logical steps exhaustively, a search space that would explode far beyond what any computer of the era, or arguably any computer today, could brute force through in reasonable time. The program used rules of thumb, heuristics, to prioritize which branches of the search tree seemed most promising, and explore those first. It didn't guarantee finding the best possible proof. It didn't even guarantee finding a proof at all, in cases where one existed, but the heuristics happened to steer the search away from it. But it made the difference between a search that might never finish and one that often did quickly, using a strategy that bore at least a family resemblance to the kind of educated guessing a human mathematician does when staring at a difficult problem, trying to sense which approach feels like it's heading somewhere. Newell and Simon followed the logic theorist with a more ambitious successor a few years later, called the general problem solver, which tried to extract the underlying strategy, the heuristic search itself, the idea of comparing your current state to your goal state and looking for operations that reduce the distance between them, and apply it not just to logic proofs, but to a much broader range of problems in principle. It was, as the name suggested, an attempt to build something closer to a general reasoning engine rather than a narrow theorem prover. The general problem solver worked, in a limited sense, on the somewhat artificial puzzle-style problems it was tested on, but it also revealed something the field would spend the next several decades gradually, sometimes painfully, coming to terms with. General-purpose reasoning turns out to be extraordinarily difficult to separate from specific knowledge about the world. A method that's genuinely useful for solving logic puzzles or the Tower of Hanoi doesn't automatically transfer to, say, understanding a sentence, or recognizing a face, or knowing that water is wet in a way that matters for planning a picnic. The general problem solver turned out to be a much heavier promise than the program could actually deliver on. It's a pattern that shows up again and again across the history of AI. This gap between a method that works beautifully on a constrained, well-defined toy problem, and the same method's much rockier relationship with the sprawling, ambiguous texture of the real world. Still, through the late 1950s and into the 1960s, the successes kept accumulating. and the optimism that had characterized the Dartmouth proposal only seemed to be gaining evidence. Arthur Samuel, an IBM researcher, built a checkers-playing program in the mid-1950s that improved through practice, adjusting its own evaluation of board positions based on the outcomes of games it played against itself. A genuinely early example of a machine that got better at something through experience rather than through a programmer directly hand-coding every improvement, and a distant ancestor, as we'll see much later tonight, of ideas that would eventually help produce systems like AlphaGo. Samuel's program eventually became strong enough to beat a reasonably skilled human amateur, and it's worth noticing that this milestone, which sounds modest today, took place on hardware that was, by any modern standard, almost unimaginably limited. A machine you'd now consider less powerful than a basic pocket calculator. Then, in the mid-1960s, a researcher at MIT named Joseph Weizenbaum built something that would end up teaching the field an uncomfortable lesson about exactly how easily people are willing to extend trust to a machine that merely seems to understand them. The program was called ELIZA, and technically, it was almost embarrassingly simple. Weizenbaum designed it to imitate a particular style of psychotherapist, specifically, a Rogerian therapist, a style built around reflecting a patient's own statements back to them as open-ended questions, rather than offering direct advice. If you typed, "I am feeling anxious about my job," Eliza might respond with something like, "Why do you say you are feeling anxious about your job?" It worked through simple pattern matching. It looked for keywords in whatever you typed, applied a small set of rules to rephrase your statement as a question, and had a handful of generic fallback responses for anything it couldn't parse at all. There was no understanding happening inside the machine in any meaningful sense. Weizenbaum knew this better than anyone because he'd written every line of it himself. What he hadn't fully anticipated was how his own secretary would react. Weizenbaum later described watching her use Eliza, and after a few exchanges, asked him to leave the room so she could continue the conversation privately. She knew, intellectually, that she was talking to a simple program. It didn't seem to matter. Something in the structure of the conversation, the reflective questions, the sense of being listened to, however mechanically that sense was actually being produced, was enough to trigger a real emotional response in a person who understood perfectly well how the trick worked. Weizenbaum found this deeply unsettling rather than encouraging, and it changed the direction of his career. He spent much of the rest of his life writing and speaking about the risks of people attributing understanding, judgment, or even a kind of therapeutic authority to systems that were, underneath the surface, doing nothing of the sort. It's a concern that has only become more relevant with time, not less. And it's worth remembering that the person who raised it most forcefully was the same person who built the program that first demonstrated the problem, using a piece of software so simple that a modern computer science student could, and often does, recreate it as a weekend exercise. Around the same period, at Stanford, other researchers were pursuing a related but more ambitious line of work. Could you build a machine that genuinely understood language, at least within some carefully limited domain, rather than merely producing the appearance of understanding through clever pattern matching? Terry Winograd, a graduate student at MIT, offered one of the most compelling answers of the era with a program called SHRDLU, completed in 1970 and named, somewhat whimsically, after a nonsense string that used to appear on old linotype printing machines. SHRDLU operated inside a very small simulated world, a tabletop containing a handful of colored blocks, pyramids, and boxes, and it could genuinely converse about that world in ordinary English sentences. You could type instructions like, "Pick up the big red block," Or put the blue pyramid on top of the block that supports the green pyramid. An SHRDLU would parse the sentence, figure out what you meant, check whether the instruction was physically possible given the current arrangement of blocks, and if so, carry it out, updating its internal model of the tabletop as it went. You could ask it questions about the past, like why it had moved a particular block, and it could answer by referring back to its own earlier reasoning. Within its tiny toy world, SHRDLU's language understanding was genuinely impressive, more impressive than almost anything that had come before it, and it generated enormous excitement about how close the field might be to general natural language understanding. But the excitement ran into the same wall the general problem solver had run into a decade earlier, just in a new form. SHRDLU's understanding was tightly, inextricably bound to its miniature block world. Its grasp of words like on, support, and move depended entirely on a simple, fully specified physical environment where every object's position and relationship to every other object was known with complete precision at all times. The moment you tried to extend that same approach to anything resembling the actual, messy, only partially specified world outside the tabletop, a world full of ambiguity, missing information, and common sense assumptions nobody had bothered to state explicitly because they seemed too obvious to need stating, the whole approach became unworkable. Winograd himself, in later years, became one of the more thoughtful critics of the assumption that scaling up SHRDLU's technique would eventually produce general understanding. Sometimes the person who builds the most convincing demonstration of an approach is also the person best positioned to see clearly where that approach runs out of road. By the early 1970s, this pattern, remarkable performance within a narrow, carefully constructed domain, followed by a much harder time extending that performance into anything broader, had repeated often enough that it started to draw serious, public scrutiny. Governments and funding agencies that had poured money into AI research through the 1960s, largely on the strength of confident promises, very much in the spirit of that original Dartmouth proposal, began asking harder questions about what exactly they'd gotten for their investment. The most damaging answer came from Britain, in a 1973 report commissioned by the country's Science Research Council and written by a mathematician named James Lighthill. And what that report concluded, and what it triggered, is where we'll go when we continue. For now, though, let it rest here for a while. A field that had spent 15 years proving theorems, playing checkers, impersonating therapists, and rearranging blocks on a table, each success narrower than it first appeared, each narrow success mistaken, a little too easily for a wider one. Everything we've talked about so far shares a common approach, even across all its variety. The logic theorist, the general problem solver, ELIZA, SHRDLU, each of them worked by manipulating symbols according to explicit rules that a human programmer had written down in advance. Words, logical statements, block positions, all represented as discrete symbols, all manipulated through handcrafted procedures. This approach even had a name, coined later, somewhat retrospectively, to distinguish it from what would eventually replace it. Symbolic AI, or sometimes, a little more evocatively, good old-fashioned AI. But there was another approach brewing during these same years, one that didn't try to encode knowledge as explicit rules at all, and it came not from logic or linguistics, but from an attempt to imitate biology directly. In 1957, a psychologist named Frank Rosenblatt, working at the Cornell Aeronautical Laboratory, built a device he called the perceptron, and it was trying to answer a fundamentally different question than the logic theorist had been. Rather than asking, "How do we write down the rules of reasoning?" Rosenblatt asked something closer to, How does a single neuron in the brain decide whether to fire? A biological neuron, in a very simplified sketch, receives signals from many other neurons, each connection carrying different strength or weight. And if the combined, weighted input crosses some threshold, the neuron fires a signal of its own. Rosenblatt's perceptron mimicked this structure directly. It took a set of numerical inputs, multiplied each one by an adjustable weight, summed the results, and if that sum crossed a threshold, it output a signal. A very simple version of the same yes or no decision a biological neuron makes. What made the perceptron genuinely new wasn't the structure itself, which was a simplified model other researchers had already sketched out theoretically. It was that Rosenblatt gave it a learning rule. If the perceptron got a classification wrong, if it was shown, say, a pattern of pixels representing a square and a pattern representing a triangle, and asked to tell them apart, and it answered incorrectly, the weights connecting its inputs would be nudged automatically in a direction that would have made the correct answer more likely. Show it enough labeled examples. Let it adjust its own weights after each mistake. And gradually, without a programmer ever writing a single explicit rule about what a square or triangle looks like, the perceptron would learn to tell them apart on its own. This was an enormous departure from everything else happening in the field at the time, and Rosenblatt, who was not a modest man, promoted it with considerable enthusiasm. The New York Times, reporting on a 1958 press conference, described the perceptron in terms that sound almost startling to read now, quoting Navy officials suggesting it would eventually be able to walk, talk, see, write, reproduce itself, and be conscious of its own existence. Rosenblatt himself was more measured in his technical papers than the press coverage suggested, but he clearly believed he had found the seed of something that would grow, with more layers and more computing power, into genuinely general intelligence. A single perceptron, though, turned out to have a very specific and very hard mathematical limitation, and the person who demonstrated it most rigorously was Marvin Minsky, one of the 4 organizers of the Dartmouth workshop 2 years after the perceptron was introduced, and as it happened, someone who had done his own doctoral work on a different kind of neural network years earlier, before shifting his interest towards symbolic approaches. In 1969, Minsky and his MIT colleague Seymour Papert published a book called Perceptrons, and in it, they proved with mathematical precision that a single-layer perceptron, the kind Rosenblatt had built and was promoting, could only learn to distinguish between patterns that were, in a specific technical sense, linearly separable. Imagine plotting your data as points on a sheet of paper, colored according to which category they belong to. A single perceptron can only ever learn a category boundary that's a straight line, or in higher dimensions, a flat plane, if the true boundary between your categories is curved, or if your categories interlock in some more complicated way. A single perceptron simply cannot represent that boundary, no matter how long you train it or how many examples you show it. It's not a matter of needing more training. It's a hard mathematical ceiling on what the architecture itself is even capable of expressing. The most famous illustration of this limitation is a small logical function called exclusivor, usually written XOR, a function that outputs true if exactly one of its 2 inputs is true, but false if both inputs are true or both are false. It's about as simple a pattern as you can construct, and a single-layer perceptron cannot learn it. Not with more data, not with more training time. The shape of the problem simply doesn't fit the shape of what the architecture can express. Minsky and Papert knew, and said so explicitly in their book, that adding additional layers to a perceptron, stacking simple units together so the output of one layer becomes the input to the next, could in principle overcome this limitation. Multi-layer networks, they acknowledged, weren't restricted to straight-line boundaries in the same way, but they were also skeptical, based on the tools available at the time, that anyone would find a practical, efficient way to train such multi-layer networks. And their book's tone, whether intentionally or not, was widely read as a broader dismissal of the entire neural network approach, rather than a narrow technical critique of one specific limited version of it. The effect on funding and research attention was severe and fairly immediate. Perceptron research, which had been attracting real money and real enthusiasm through the early and mid-1960s, largely dried up for over a decade. It's a slightly uncomfortable footnote to this part of the story that Minsky, a leading figure in the symbolic AI camp, had just written the book that effectively sidelined his field's main rival approach for the next 10 to 15 years. And it's worth being careful here, because the popular version of this story sometimes overstates how deliberate or vindictive this was. Minsky and Papert's mathematics was correct, and it addressed real, genuine limitations. But the chilling effect it had, whatever the intent behind it, was real too, and it would take a very different set of researchers, working with a very different training method, to eventually show that Minsky and Papert's own acknowledged escape route, multiple layers, could actually be made to work. We'll get to that. It's one of the more satisfying turns in this whole story, but it's still a couple of decades away from where we are right now. Meanwhile, the symbolic side of the field, which had survived the perceptron controversy relatively unscathed, was about to face its own reckoning. And this one wasn't a matter of mathematical proof. It was a matter of money running out. In 1973, the British government, growing increasingly skeptical about the return on over a decade of AI funding, commissioned a report from James Lighthill, a distinguished applied mathematician who, notably, was not himself an AI researcher. Lighthill's report divided AI research into 3 categories and concluded that progress in the most ambitious category, what he called advanced automation, roughly corresponding to general-purpose reasoning and understanding, had been deeply disappointing relative to the confident promises the field had been making since Dartmouth. He was particularly critical of what he described as the field's tendency to solve small, artificial toy problems, much like SHRDLU's block world, while treating that success as meaningful progress toward much larger, much harder real-world problems, when in fact the gap between the two, in his assessment, hadn't meaningfully closed at all. The report led directly to a BBC-televised debate, held later that year, pitting Lighthill against 3 prominent AI researchers. And while the debate is now something of a historical curiosity, the practical consequence was much less theatrical and much more damaging. The British government slashed AI research funding at all but a couple of universities almost immediately. And because British and American funding agencies paid close attention to each other's decisions, similar reductions followed in the United States over the next few years, as agencies like DARPA grew impatient with a field that had promised, repeatedly, more than it had delivered on any realistic timeline. This period, stretching roughly from the mid-1970s into the early 1980s, later became known, somewhat wryly, as the first AI winter, a term borrowed deliberately from the much more alarming concept of nuclear winter, which gives you some sense of how bleak researchers in the field felt things had become. Funding contracted. University departments quietly stopped using the phrase artificial intelligence in grant proposals, preferring blander, less politically loaded terms like informatics or machine learning. Even when the underlying research hadn't changed at all, just the label attached to it, a small but telling detail about how thoroughly the field's name had become, for a while, something of a liability rather than an asset. But winters end. And this one ended because of a genuinely new idea, or rather, an old idea from the mainframe era of computing repackaged for a new decade, one that would produce, for a brief and genuinely lucrative stretch of the 1980s, something the field hadn't really had before: actual commercial products that actual companies were willing to pay real money for. The idea behind what became known as expert systems was, in retrospect, fairly intuitive, even if building one well turned out to be much harder than it first appeared. If you can't yet build a machine with broad, general intelligence. And by the mid-1970s, it was becoming painfully clear that nobody was close to that. Perhaps you could still build something narrower and more useful. A machine that captured the specific, specialized knowledge of a human expert in one particular field, encoded as a large collection of if-then rules, and applied that knowledge to new cases the way a human expert would. One of the earliest and most influential examples came out of Stanford in the early 1970s, a program called MYCIN, developed primarily by Edward Shortleff, aimed at helping physicians diagnose bacterial infections and recommend appropriate antibiotics. MYCIN worked by asking the user a series of questions about a patient's symptoms, test results, and medical history, and then applying several hundred handcrafted rules. The kind of rules a specialist in infectious disease might describe if you asked them to explain their own diagnostic reasoning out loud, step by step. Crucially, MYCIN didn't just spit out a diagnosis with false confidence. It attached a numerical certainty factor to its recommendations, and perhaps more importantly for winning over skeptical physicians, it could explain its own reasoning if asked, tracing back through the specific chain of rules that had led to a given conclusion. In carefully controlled evaluations, MYCIN's recommendations were judged by panels of independent experts to be at least comparable to the recommendations of practicing physicians, and in some assessments, slightly better. It was never actually deployed in real clinical settings, partly due to legal and ethical concerns about a machine making medical recommendations decades before anyone had really worked out how liability should function in that situation. But it stands as one of the clearest early demonstrations that a machine, without anything resembling general understanding, could still capture genuinely valuable specialized expertise. A related program, DENDRAL, developed slightly earlier at Stanford by Edward Feigenbaum, Bruce Buchanan, and the Nobel Prize-winning geneticist Joshua Lederberg, tackled a different specialized problem. Given raw data from a mass spectrometer, a piece of laboratory equipment that breaks organic molecules apart and measures the resulting fragments, could a machine work backward and determine the molecular structure of the original compound? This is a task that, at the time, required years of specialized chemistry training to do well, and DENDRAL, encoding the accumulated expertise of working chemists as a set of rules, could do it too, quickly and often correctly, on classes of molecules its rules had been designed to handle. What Feigenbaum, in particular, took from this success was an idea he articulated explicitly, and which came to define the whole expert systems movement. He called it the knowledge is power hypothesis, and the argument was straightforward, even if the engineering to support it was not. Intelligent behavior, he argued, doesn't require some deep, mysterious, general reasoning capacity. It mostly requires a large amount of specific, well-organized domain knowledge, applied through a reasonably simple inference mechanism. Get the knowledge right, encode enough of it, and the intelligence follows almost automatically. It's a genuinely different bet than the one Rosenblatt had made with the perceptron a decade earlier. Rosenblatt was betting that intelligence would emerge from a simple learning mechanism exposed to enough data, while Feigenbaum was betting that intelligence required painstakingly hand-encoding what human experts already knew. Both bets, it's worth noting quietly here, would eventually turn out to be partly right and partly wrong, in ways that took decades longer to sort out than anyone involved expected. Through the late 1970s, and especially the 1980s, the expert systems approach moved out of research labs and into industry with real commercial momentum. Digital Equipment Corporation, a major computer manufacturer, deployed a system called XCON starting in 1980, designed to configure the specific components needed for each customized order of their VAX computer systems. A genuinely complicated task, since customers could order these machines with an enormous number of possible combinations of processors, memory units, cabinets, and cables, and getting a configuration wrong meant expensive re-engineering after the fact. XCON eventually grew to encompass several thousand rules and was credited with saving the company tens of millions of dollars annually by reducing configuration errors, which is precisely the kind of unglamorous, specific, bottom-line result that convinced a lot of otherwise skeptical corporate executives that this AI thing might actually be worth investing in. Whatever had happened during the previous decade's disappointments, this commercial success fed a specialized hardware industry that, viewed from today, seems almost quaintly narrow. Companies like Symbolics and Lisp Machines incorporated built and sold computers specifically optimized to run Lisp, the programming language of choice for most expert systems and symbolic AI research generally, since Lisp's structure made it particularly well-suited to manipulating the kind of symbolic rules these systems relied on. These machines were expensive, specialized, and for a few years in the early to mid-1980s, genuinely profitable businesses. Governments took notice too, and Japan, in particular, launched an ambitious national research initiative in 1982 called the Fifth Generation Computer Systems Project, committing several $100 million over a planned 10-year period toward building a new generation of computers designed from the ground up around logic programming and knowledge-based reasoning, with the explicit goal of leapfrogging the United States and Europe in what Japanese planners saw as the coming era of intelligent machines. The announcement alarmed American and British policymakers enough that it helped justify renewed, if more cautious, government funding for AI research in their own countries. A reminder that competitive anxiety between nations has, more than once in this story, done as much to open research funding as any specific scientific breakthrough. But the expert systems boom, like the symbolic optimism of the 1960s before it, ran into structural problems that no amount of additional funding could fully solve. And by the late 1980s, those problems were becoming impossible to ignore. Expert systems were extraordinarily brittle. They performed well, sometimes excellently, within the exact boundaries of the knowledge their rules encoded, but they had no meaningful way to handle situations even slightly outside those boundaries. And worse, they generally had no good way of recognizing that they'd wandered outside their competence at all. A system built to diagnose bacterial infections would confidently apply its rules to a case involving a condition its rules had never been designed to consider, and produce a confident, plausible-sounding, entirely wrong answer, with no internal signal indicating that anything had gone wrong. Humans, even non-expert humans, tend to have some intuitive sense of the edges of their own knowledge. Expert systems built from explicit rule lists generally didn't, unless a programmer had specifically anticipated that particular gap and written a rule to handle it, which meant the engineering effort required to make these systems robust grew, roughly, in proportion to how many edge cases the world could throw at them, which is to say, it grew essentially without bound. There was also a deeper, more structural problem, one that came to be called the knowledge acquisition bottleneck. Building an expert system required sitting down with human experts and painstakingly extracting their knowledge, rule by rule, through extensive interviews. A slow, expensive, and often surprisingly difficult process, partly because genuine experts frequently can't fully articulate their own reasoning. A skilled physician or chemist often makes correct judgments based on pattern recognition built up over years of experience, a kind of intuition that resists being cleanly translated into explicit if-then statements, no matter how patient the interviewer. You can ask an expert why they reached a particular conclusion, and they'll often give you a reasonable-sounding explanation after the fact. But that explanation may not actually correspond to the real cognitive process that produced the judgment in the first place. This made building and, worse, maintaining these systems enormously labor-intensive. And as rule bases grew into the thousands, they became difficult even for their own creators to fully understand or safely modify, since a small change to one rule could produce unexpected interactions with hundreds of others. By 1987, the market for specialized Lisp machine hardware collapsed almost overnight, undercut by general-purpose workstations from companies like Sun Microsystems that had grown powerful enough to run Lisp software adequately without needing dedicated hardware, at a fraction of the cost. Symbolics, once a genuinely successful company, went bankrupt. The fifth-generation project in Japan wound down by the early 1990s without having achieved most of its original, ambitious goals. Corporate enthusiasm for expensive, brittle, hard-to-maintain expert systems curdled fairly quickly into disillusionment. And government funding agencies, watching the pattern repeat almost exactly as it had 15 years earlier under Lighthill, once again grew skeptical and began pulling back. This second contraction, running roughly from the late 1980s through much of the 1990s, became known as the second AI winter. And it was, in some ways, more discouraging than the first, precisely because it followed a period of genuine commercial success rather than pure academic promise. The field had actually delivered real products, real profits, real deployed systems, and it still hadn't produced anything resembling the general intelligence that had been the whole point of the enterprise since that summer at Dartmouth over 30 years earlier. What's easy to miss, looking back at this period from the outside, is that this wasn't actually a quiet time for the field's underlying research, even if it felt that way to anyone watching funding levels or reading newspaper coverage. Away from the collapsing expert systems industry, in labs that had mostly stopped calling their work artificial intelligence at all, a small number of researchers were quietly finishing something that Minsky and Papert had, all the way back in 1969, acknowledged might theoretically be possible, but doubted anyone could practically achieve: a reliable way to train neural networks with more than one layer. That's where we're headed next, and it's worth staying awake for just a little longer, because this next part is the hinge the entire rest of the story swings on. Imagine for a moment a very long factory line. Not a metaphor for a neural network yet, just a factory line, the kind that makes something ordinary like a chair. Raw wood goes in one end. A finished chair comes out the other. Along the way, dozens of workers each perform one small operation, and each worker's output becomes the next worker's input. Someone cuts the legs to length, someone else sands them, someone else attaches them to the seat, someone else applies the finish on and on, down a long chain. Now suppose the finished chair wobbles. One leg is very slightly shorter than the other three. Somewhere down that long chain, a mistake was made, but the wobble only becomes visible at the very end, after the chair is fully assembled. How do you figure out which worker, at which station, made the error that caused it? You could, in theory, walk backward down the line. Look at the finished chair, notice the wobble, and ask, Given what I know about how each station affects the final product, which station is most likely responsible, and by how much? The final assembly worker who attached the legs might be blameless. They attached exactly what they were given. The problem might trace back to the person who cut the legs, or further back still, to whoever calibrated the saw that person was using. Tracing the error backward, one station at a time, apportioning responsibility appropriately at each step, is a fundamentally different task than watching the line run forward. It requires understanding, at each station, how a small error at that station would have propagated forward and affected everything downstream of it. This is, in essence, the problem that made multi-layer neural networks so difficult to train for the better part of 3 decades. And it's also, in essence, the problem that backpropagation eventually solved. Recall Rosenblatt's original perceptron. Inputs, weights, a sum, a threshold, and output. A single layer, effectively a single worker station. When that single perceptron got something wrong, adjusting the weights was reasonably straightforward because there was only one station to blame, and you could measure directly how much each input had contributed to the mistaken output. But stack several layers of these simple units together. The escape route Minsky and Papert had acknowledged, in principle, might overcome the perceptron's limitations, and the problem becomes much harder. Now you have a whole chain of stations. Input signals pass through the first layer, get transformed, pass through a second layer, get transformed again, and so on until a final layer produces an output. When that final output is wrong, which layer's weights should you adjust, and by how much? The final layer clearly played some role, but so did every layer before it, and the contribution of an early layer to a final mistake is filtered through everything that happened to its output on the way downstream. It's the wobbly chair problem, except instead of 4 or 5 factory stations, you might have thousands of individual connections, each one a small weight that needs to be nudged in exactly the right direction, and by exactly the right amount. The mathematical tool needed to trace responsibility backward through a chain like this already existed, and had existed for centuries, tucked away in calculus, under the name the chain rule. The same basic principle for working out how a change at one stage of a multi-step process ripples through to affect the final result. What was missing wasn't the mathematics itself. It was the recognition that this particular piece of mathematics could be applied, systematically and efficiently, to the specific problem of training layered networks of these simplified artificial neurons. The first person to work this connection out in real detail, in the specific context of training networks, was a Harvard doctoral student named Paul Werbos, who described the method in his 1974 dissertation. Werbos's work sat almost entirely unnoticed for over a decade, partly because it was published during the very depths of the funding retreat that followed the Lighthill Report, when almost nobody in the field was paying close attention to neural network research at all, and partly because dissertations, even excellent ones, don't always find their way to the people who most need to read them. The idea resurfaced, and this time it stuck, in 1986, in a paper written by David Rumelhart, Jeffrey Hinton, and Ronald Williams, published in the journal Nature under the title Learning Representations by Backpropagating Errors. Hinton, in particular, would go on to become one of the most influential figures in the entire subsequent history of the field. And it's worth noting, since we're telling this story slowly and without rushing to any single conclusion, that the 1986 paper's core mathematical idea wasn't actually new. Werbos had it first, and a few other researchers had independently stumbled onto related pieces of it too. What the Rumelhart, Hinton, and Williams paper did, and did remarkably well, was demonstrate the method's power clearly, apply it to problems that made its usefulness vivid and intuitive, and present it in a way the wider research community could immediately understand and start using themselves. Sometimes the history of an idea and the history of an idea's adoption are two genuinely different stories. And this is one of the clearer examples of that gap in the whole history of the field. So here, finally, is how backpropagation actually works, walked through slowly. A neural network, in its most basic form, is a chain of layers, each one containing a number of simple units loosely inspired by neurons, each unit connected to units in the layer before it through a weight. A single adjustable number representing how strongly that connection should influence the receiving unit. You feed data in at one end, say, the pixel values of an image, and it flows forward through the network, layer by layer, each layer's units computing a weighted sum of their inputs and passing the result onward, until you reach the final layer, which produces the network's answer. This image is a cat, say, or this image is a dog. If the network is wrong, if it confidently says dog when the image was actually a cat, you can measure exactly how wrong it was, using what's called a loss function, essentially a formula that produces a single number representing the size of the mistake. A small loss means the network was close. A large loss means it was way off. Backpropagation is the procedure for taking that single loss number, sitting at the very end of the network, and tracing it backward through every layer, computing, at each connection along the way, exactly how much that particular weight contributed to the final error, and in which direction it should be nudged to make the error smaller next time. It does this using the chain rule, applied layer by layer, moving from the output backward toward the input, hence the name. The output layers' weights get adjusted first, based on their direct contribution to the loss. Then, using information about how the output layer's inputs relate to the loss, the method works out how the second-to-last layer's weights should be adjusted. Then the layer before that, and so on, all the way back to the very first layer, each layer's adjustment informed by everything that happened downstream of it. It's worth sitting with why this backward tracing approach is so much more efficient than the alternative, because the efficiency is really the whole point. You could, in principle, try to figure out how each individual weight affects the final loss by nudging that one weight slightly, rerunning the entire network forward, and seeing how much the loss changed, and then repeating that process, one weight at a time, for every single weight in the network. For a network with even a modest number of connections, this would be catastrophically slow, since you'd need a full forward pass through the entire network for every single weight you wanted to check. Backpropagation, by contrast, computes the necessary information for every weight in the network using just one forward pass to compute the output, and one backward pass to distribute the blame. A single round trip through the network, regardless of how many weights it contains. It's the difference between checking a chair for wobble by disassembling and reassembling the entire thing separately for every single joint, versus doing one careful inspection and working out, from first principles, exactly how each joint's angle contributed to the final wobble, all in one pass. Once you can efficiently compute how every weight in a multi-layer network should be adjusted to reduce a given error, training the network becomes a matter of repetition. Show it an example. Let the signal flow forward. Measure the error. Trace the blame backward. Nudge every weight very slightly in the direction that reduces the error. Repeat thousands of times, tens of thousands of times, often with many different training examples mixed together in batches to keep any single adjustment from overcorrecting based on one unusual case. Each individual nudge is tiny, almost imperceptibly small, but the accumulated effect over enough repetitions is a network that has gradually reshaped its own internal weights until its outputs, on the training examples at least, become reliably close to correct. And here, at last, is the payoff to a thread we planted several chapters ago, back when Minsky and Papert proved that a single perceptron couldn't learn the XOR function, couldn't separate categories that weren't cleanly divided by a straight line. A network with even one additional hidden layer between input and output, trained with backpropagation, can learn XOR without any difficulty at all. The extra layer gives the network room to build up an internal representation, a reshaped version of the input, constructed by the first layer, that transforms the tangled, non-linearly separable original problem into something the following layer can handle with a simple straight-line boundary after all. Stack more layers, and the network can build up increasingly abstract internal representations, each layer transforming the output of the one before it into something a little more useful for the task at hand. The escape route Minsky and Papert had acknowledged back in 1969, but doubted anyone could practically realize, turned out to be entirely realizable. It just took someone working out how to efficiently assign blame across many layers at once, using a mathematical idea that had, in one form or another, been sitting quietly in calculus textbooks since the 18th century. It's a nice, slightly ironic detail if you want to hold on to it as you drift. The mathematics that finally let machines learn in layers wasn't new mathematics at all. It was old mathematics, waiting patiently for someone to notice it fit a new problem. Backpropagation didn't immediately trigger the explosion of neural network research you might expect, given how central it eventually became. Through the late 1980s and into the 1990s, it remained one useful technique among several competing approaches, and it ran into a real and serious practical limitation that would take another 2 decades and an entirely different kind of hardware to properly overcome. A limitation we'll get to a little later tonight, once we've talked about what these networks are actually made of, piece by piece. So the later limitation makes more intuitive sense when we get there. It's worth slowing down here and building up, carefully and without hurrying, exactly what a neural network is made of, because everything from this point forward in the story, every architecture, every breakthrough, every headline you may have half read about some new system doing something remarkable, is, underneath all its complexity, a variation on the same small set of basic parts we're about to walk through. Start with a single artificial neuron, sometimes called a unit or a node, and don't picture anything biological, even though the name invites the comparison. Picture instead a very small calculator with a specific, fixed job. It receives a number of inputs. These might be raw data, like the brightness values of pixels in an image, or they might be the outputs of other neurons earlier in the network. Each input arrives along a connection that has its own weight, a single number that determines how much influence that particular input should have. A large positive weight means that input strongly pushes the neuron toward firing. A large negative weight means that input strongly pushes it the other way. A weight near zero means that input barely matters at all to this particular neuron, regardless of what value it carries. The neuron multiplies each input by its corresponding weight, adds all those products together, and then adds one more number, called the bias, which you can think of as the neuron's baseline tendency, its willingness to fire even before it's seen any input at all. A permanently thumb-on-the-scale adjustment that shifts the whole calculation up or down. If the story stopped there, though, stacking these neurons in layers wouldn't actually gain you anything. And this is a genuinely important, slightly counterintuitive point worth sitting with. A weighted sum followed by another weighted sum is still, mathematically, just another weighted sum. You could always collapse any number of purely linear layers back down into a single equivalent layer, and you'd be right back to the same straight-line boundary limitation that doomed Rosenblatt's original single-layer perceptron. Depth, by itself, buys you nothing if every layer is doing nothing but multiplying and adding. What actually gives depth its power is a small but essential extra step applied at each neuron, after the weighted sum and bias have been calculated. An activation function, a rule that takes that combined number and bends it non-linearly into the neuron's actual output. Early networks, including Rosenblatt's, often used a simple threshold. If the sum crosses a certain value, output 1. Otherwise, output 0, mimicking the abrupt, all-or-nothing firing of a biological neuron. But that hard, sudden jump turns out to be mathematically awkward for backpropagation, because a chain rule calculation needs to measure how the output changes as you make tiny adjustments to the input, and an abrupt threshold, by definition, doesn't change smoothly. It's either fully off or fully on, with nothing informative happening in between. So researchers turned to smoother activation functions instead. One common early choice was the sigmoid function, which produces a smooth S-shaped curve, squeezing any input, however large or small, into an output that always falls somewhere between 0 and 1, changing gradually rather than jumping abruptly. Another, called the hyperbolic tangent, does something similar but ranges between -1 and +1. Both of these functions, crucially, are nonlinear, bent rather than straight, which is precisely the property that lets stacked layers actually build on each other's work rather than collapsing back down into a single equivalent linear layer. Each layer, using its nonlinear activation, can carve the problem into a slightly different, slightly more useful shape than the layer before it received. And by the time information has passed through several such layers, the network has effectively transformed the original, tangled problem into something its final layer can resolve with something as simple as a straight-line decision after all. A layer, then, is just a collection of these individual neurons, all receiving the same set of inputs from the layer before, each one applying its own particular weights, bias, and activation function to produce its own particular output, which then becomes part of the input for the next layer in the chain. The very first layer, which receives the raw data, is called the input layer. The very last layer, which produces the network's final answer, is called the output layer. Everything in between is called a hidden layer, a name that sounds more mysterious than it really is. Hidden simply means that a human observer doesn't directly see or interpret what these intermediate layers are computing, unlike the clearly labeled input and output. A network is called deep, in the sense that gives deep learning its name, simply when it has a meaningful number of these hidden layers stacked between input and output. Not one deep insight, just several layers deep. What's genuinely worth pausing on, because it's one of the more quietly remarkable facts about how these networks behave, is what tends to happen inside those hidden layers once a network has been trained on a real task, like recognizing images. Nobody tells the network explicitly what each hidden layer should be looking for. The weights start out essentially random, and backpropagation simply nudges them, repeatedly, in whatever direction reduces the final error. And yet, when researchers have opened up trained networks and examined what individual units in early hidden layers respond most strongly to, they've often found something that looks a great deal like edge detection. A unit that fires strongly when it sees a sharp light-to-dark transition at a particular angle and stays quiet otherwise. Units in slightly deeper layers often respond to combinations of edges, simple textures, or curves or corners. Deeper still, in networks trained on complex enough images, researchers have found units that seem to respond to entire recognizable parts of objects, something that fires reliably in the presence of what looks like an eye, or a wheel, or a patch of fur. Nobody designed this hierarchy on purpose, at least not at the level of individual units. It emerged, layer by layer, as a natural consequence of a network trying to reduce its error on the task it was given, discovering, through nothing more than repeated small adjustments guided by backpropagation, that building up from simple features to increasingly complex ones happens to be an efficient way to solve the underlying problem. It's a small, quiet echo of something we noticed all the way back in the very first chapter of this story, with the Jacquard loom and Babbage's analytical engine. The idea that complex, apparently purposeful behavior can emerge from a large number of very simple operations, correctly arranged. The difference this time is that nobody arranged them. The arrangement itself was learned. This particular observation, that early layers tend to detect simple features and later layers tend to detect increasingly complex combinations of those features, turns out to matter enormously for a specific class of network we haven't discussed yet, one designed quite deliberately to take advantage of the fact that images, in particular, have a kind of structure that ordinary, fully connected layers handle rather wastefully. That's where we'll go when we continue. A French researcher who spent the tail end of the second AI winter working, mostly quietly, on a way of building networks that mirrored something already well understood about how biological vision itself seems to work. Decades before anyone was training neural networks at all, two neurophysiologists named David Hubel and Torsten Wiesel ran a long series of experiments on cats, recording the activity of individual neurons in the visual cortex while showing the animals simple patterns of light. What they found, published across the late 1950s and 1960s, was that individual neurons in the earliest visual processing areas didn't respond to the image as a whole. Each one responded only to a very small patch of the visual field, and only to specific simple features within that patch. A bar of light at one particular angle, in one particular location, and nothing else. Move that same bar of light to a different location, and a different neuron, tuned to that different patch, would be the one to respond. Only in later stages of visual processing did the brain begin combining these small, localized detections into a representation of larger shapes and eventually whole objects. Yann LeCun, a French researcher working through the 1980s, first at a small lab in Paris and later at Bell Labs in the United States, took this biological finding as an architectural clue rather than just a curiosity. If the visual cortex processes images by scanning small local patches for simple features, and only later combining those detections into larger structures, perhaps an artificial network built to solve visual tasks should be structured the same way. Rather than treating every pixel as an independent input feeding into a single sprawling, fully connected layer, the architecture LeCun developed, which came to be called a convolutional neural network, worked by sliding a small grid of weights, called a filter, or a kernel across an image, patch by patch, applying that same small set of weights at every location. If the filter had learned to detect, say, a diagonal edge, it would apply that exact same edge-detecting calculation to every patch of the image in turn, producing a map showing where diagonal edges appeared anywhere in the picture. This is called weight sharing, and it solves a real, practical problem that a plain, fully connected network handles rather clumsily. Recognizing a cat shouldn't require learning what a cat's ear looks like separately for every possible position that ear might occupy in the frame. A convolutional layer learns to detect a feature once, and then applies that same detector everywhere, which dramatically reduces the number of separate weights the network needs to learn, and means the network can recognize a feature regardless of where in the image it happens to appear. After a convolutional layer detects features across an image, a second kind of layer, called pooling, typically follows, and its job is to shrink the resulting feature maps down, keeping only the strongest signal from each small local region and discarding the rest. This makes the network progressively less sensitive to exactly where a feature appeared and more sensitive to whether it appeared at all, which turns out to be exactly the right trade-off for recognition tasks. Stack several rounds of convolution and pooling together, and you get, quite naturally, the same hierarchy we noticed emerging in the previous chapter: early layers detecting simple edges and textures, deeper layers combining those into increasingly complex shapes, and eventually recognizable object parts. Except now that hierarchy has an architecture specifically designed to make it efficient, rather than emerging, more slowly and wastefully, from a generic structure trying to reinvent the same idea from scratch. LeCun's most famous early system, developed through the late 1980s and refined into the 1990s, and generally known as LeNet, was trained to read handwritten digits, and it found a genuinely practical, unglamorous, and quite lucrative home doing exactly that, reading the handwritten numbers on checks for American banks, and later, handwritten zip codes for postal sorting. It's worth noticing, because it's a pattern that recurs throughout this history, that one of the earliest deployed successes of deep learning wasn't a dramatic public demonstration at all. It was quiet, unglamorous infrastructure, sorting mail and processing checks, doing one specific job extremely reliably, largely unnoticed by anyone outside the banking and postal industries that depended on it. But through the late 1990s and into the 2000s, convolutional networks, like neural networks generally, remained somewhat overshadowed by other approaches that were, for the moment, easier to train reliably and less demanding of computing resources the field simply didn't have much access to yet. What changed, and changed quite suddenly, arrived from two directions at once, and it's where we'll go next. Training a deep network well requires two things in abundance, and through most of the 1990s and 2000s, the field had a real shortage of both. The first is data, a large number of labeled examples the network can learn from, since backpropagation only works by comparing the network's guesses against known correct answers, over and over, gradually refining its weights. For most of the field's history, assembling large, carefully labeled datasets was itself a slow, expensive, mostly manual undertaking. A researcher named Fei-Fei Li, then at Princeton and later Stanford, addressed this directly starting around 2006 with a project that seems almost audacious in retrospect. Rather than building a modest dataset of a few thousand labeled images, as had been typical, she set out to build one spanning millions of images across thousands of categories, organized according to an existing linguistic hierarchy of nouns. The resulting dataset, called ImageNet, was assembled partly through crowdsourced human labor, verifying and sorting an enormous number of candidate images, a genuinely massive undertaking that took years to complete. Starting in 2010, Lee and her collaborators turned ImageNet into an annual public competition, challenging research teams to build the most accurate image classification system they could, tested against a held-out portion of this enormous, carefully labeled collection. The second missing ingredient was raw computing speed, and the solution to that shortage arrived, somewhat unexpectedly, from an entirely different industry: video games. Graphics processing units, or GPUs, had been developed and refined over the 1990s and 2000s for an extremely specific purpose: rendering the millions of small, repetitive geometric calculations needed to draw a video game's three-dimensional world onto a screen, dozens of times per second. Unlike a computer's main processor, which is built to handle a wide variety of different tasks quickly, one or a few at a time, a GPU is built to perform an enormous number of simple, similar mathematical operations all at once, in parallel. And it turns out, almost as a coincidence of engineering history, that the core mathematical operation inside a neural network, multiplying large grids of numbers together, over and over, layer after layer, is structurally almost identical to the core operation involved in rendering three-dimensional graphics. A piece of hardware built to draw explosions and character models in a video game turned out to be extraordinarily well-suited to training neural networks, requiring only that someone repurpose it for the job. These two threads converged decisively in 2012 when a graduate student named Alex Krzyzewski, working with Ilya Sutskever and their supervisor Jeffrey Hinton, the same Hinton from the 1986 backpropagation paper, still very much active in the field decades later, entered that year's ImageNet competition with a deep convolutional network trained using GPUs that came to be called AlexNet. The result wasn't a narrow, incremental improvement over the competition's previous years. It was a rout. AlexNet's error rate was roughly 10 percentage points better than the next best entry, a margin that stunned a research community accustomed to competitions being decided by fractions of a percent. What made AlexNet possible wasn't a fundamentally new idea. The convolutional architecture LeCun had developed decades earlier was, at its core, the same basic design. What had changed was that ImageNet finally provided enough labeled data to train a large network without it simply memorizing a small dataset uselessly. And GPUs finally provided enough raw computing speed to train a genuinely deep network on that much data within a practical amount of time. Training that would have taken months or years on the processors available even a decade earlier could now be done in about a week. The effect on the field was immediate and, in retrospect, obviously permanent. Within just a few years of AlexNet's 2012 result, nearly every serious computer vision research group had shifted to deep convolutional networks, and the broader lesson that neural networks, given enough data and enough compute, could reliably outperform approaches that had taken decades of careful, handcrafted engineering to build, began spreading well beyond vision into every other corner of the field where researchers had access to large datasets and, increasingly, cheap GPU time to draw on. One of those other corners was language, and it turned out to need an idea that convolution alone couldn't give it. A photograph doesn't unfold over time. All of its pixels exist at once, simultaneously, arranged in a fixed grid, which is exactly the kind of structure convolutional networks were built to exploit. A sentence is different. Its words arrive in sequence, one after another, and their meaning depends heavily on that order. The dog bit the man, and the man bit the dog contain identical words and mean entirely different things. Any network meant to work seriously with language needed some way of handling this sequential structure, some sense of what had come before. The earliest serious attempt at this, called a recurrent neural network, tried to solve the problem by giving the network a kind of memory. Rather than processing an entire input all at once, a recurrent network processes a sequence one element at a time, one word, say, and at each step, it combines that new word with a summary of everything it has processed so far, updating that summary as it goes and carrying it forward to the next step. In principle, this lets information from early in a sentence influence how the network interprets something much later in the same sentence, which is exactly the kind of long-range dependency ordinary language is full of. In practice, though, recurrent networks ran into a specific, stubborn version of a problem we've actually already discussed, back when we first explained backpropagation. Training a recurrent network means tracing the chain rule backward not just through layers, but through every single time step in a long sequence. And if a sentence is long enough, that backward chain becomes very long indeed. Each step in that chain involves multiplying by some factor. And if those factors tend to be smaller than 1, which they very often are, multiplying many of them together in a row produces a result that shrinks towards 0 extremely quickly, meaning the influence of early words on the network's learning essentially evaporates before the backward pass ever reaches them. This is called the vanishing gradient problem, and it meant early recurrent networks were, in practice, quite forgetful, reliably losing track of anything that had happened more than a handful of words earlier. A partial fix arrived in 1997 from 2 researchers named Sepp Hochrader and Eugen Schmidhuber in the form of an architecture called long short-term memory, or LSTM. Rather than forcing information to pass through the same repeated multiplication at every single step, an LSTM includes a dedicated internal pathway, sometimes described as a memory cell, along with small learned gates that control, at each step, how much old information should be kept, how much new information should be let in, and how much should be output. These gates let the network learn from data when to hold onto something important from many steps earlier, and when to let it fade, largely sidestepping the vanishing gradient problem that had crippled simpler recurrent designs. LSTMs became, for the better part of 2 decades, the dominant tool for any task involving sequences, speech recognition, machine translation, text generation, and they worked genuinely well. They were also, structurally, quite slow to train, because their whole design depends on processing a sequence 1 step at a time, in strict order, which makes it very hard to take advantage of the kind of massive, all-at-once parallel computation that had just made GPUs so transformative for convolutional networks. Around the same period, a separate and initially unrelated idea was changing how networks represented the meaning of individual words in the first place. Traditionally, a word fed into a network had to be represented somehow as numbers, and the crudest approach simply assigned each word in a vocabulary its own arbitrary numerical slot, with no relationship at all between the numbers for, say, king and queen, or between queen and throne. In 2013, a team at Google led by Tomas Mikolov introduced an approach called word-to-vec, which instead trained a simple network to predict a word from its surrounding context, across a huge amount of ordinary text, and then discarded the prediction task itself, and kept only the internal numerical representation. The network had learned to assign each word along the way. What emerged, almost as a side effect, was startling. Words that tended to appear in similar contexts ended up with similar numerical representations, positioned near each other in a high-dimensional mathematical space. And the geometric relationships between those positions turned out to capture something genuinely meaningful about the relationships between the words themselves. The now well-known demonstration involved taking the numerical representation for king, subtracting the representation for man, adding the representation for woman, and finding that the resulting point in that space landed very close to the representation for queen, meaning had become, in some real mathematical sense, a matter of geometry, direction, and distance, learned entirely from patterns of word co-occurrence, with nobody ever telling the network what a king or a queen actually was. By the mid-2010s, then, the field had 2 powerful but separately limited tools for language: LSTMs, which handled order and long-range dependency reasonably well, but were slow and still somewhat forgetful over very long stretches of text, and word embeddings, which gave individual words rich, meaningful numerical representations, but said nothing on their own about order or relationships between words in a specific sentence. What the field still lacked was a way to let every word in a sentence directly consider every other word, all at once, regardless of how far apart they were, without being forced through the slow, one-step-at-a-time bottleneck that recurrence required. The answer arrived in 2017, in a paper from a team of researchers at Google with the almost cheekily blunt title, "Attention is all you need." And the architecture it introduced, called the transformer, has since become the foundation underneath essentially every major language model you may have heard of. The central idea is called self-attention, and it's worth walking through slowly, because the underlying mechanism, stripped of jargon, is genuinely intuitive. For every word in a sentence, the network calculates a score describing how relevant every other word in that same sentence is to correctly interpreting this one, not based on distance, but based on learned relationships between the word's meanings and roles. Consider the sentence, "The trophy didn't fit in the suitcase because it was too big." To understand what it refers to, a reader needs to connect that word back to trophy, not suitcase, which requires understanding something about the physical relationship the sentence is describing, not just proximity on the page. It sits right next to suitcase, but it doesn't refer to the suitcase. Self-attention lets the network learn to make exactly this kind of connection, computing, for every word, a weighted blend of every other word in the sentence, with the weights determined by how relevant each of those other words actually is to interpreting this one, regardless of how many words separate them. Because this calculation can be done for every word simultaneously, rather than one step at a time in sequence, transformers sidestep the slow, forced-order bottleneck that had limited LSTMs, and they turn out to be extremely well-suited to exactly the kind of massive parallel computation GPUs are built for. A transformer processing an entire paragraph can, in principle, examine every word's relationship to every other word all at once, in a single sweep, rather than laboriously carrying a single narrow summary forward one word at a time, and hoping nothing important gets lost along the way. Stack several layers of this self-attention mechanism together, each layer building a progressively richer representation of how the words in a passage relate to one another, echoing, once again, the same hierarchy of representations theme that's run through this entire story since convolutional networks first learned to stack edges into shapes and shapes into objects. And you arrive at an architecture capable of representing, with real nuance, the structure and meaning of extended passages of text. It's this architecture, scaled up dramatically in both size and in the sheer volume of text it's trained on, that underlies the large language models that would, within just a few years of the Transformers' introduction, become capable of holding a conversation that, for the first time in the history of this whole pursuit, could genuinely make Turing's old imitation game a live, practical question rather than a thought experiment. That's where we're headed next. The task researchers settled on for training these new transformer-based language models was, on its face, almost absurdly simple. Given a stretch of text, predict the next word. That's essentially it. Feed the model an enormous amount of text drawn from books, articles, and the wider internet. Hide the actual next word at each point, and let the network guess, adjusting its weights through backpropagation, exactly as we described several chapters ago, whenever it guesses wrong. Do this across billions of words and repeat. What made this simple task so powerful was that predicting the next word well, across a sufficiently vast and varied body of text, turns out to require the model to implicitly capture an enormous amount of structure about the world the text describes. Grammar, certainly, but also facts, patterns of reasoning, conventions of argument, even something resembling common sense. Because all of these things leave statistical fingerprints on which word is likely to come next in a given context. A model that's genuinely good at predicting text has, in some real sense, had to absorb a compressed model of a great deal of what that text was actually about. Researchers at OpenAI pursued this approach across a series of models generally known by the acronym GPT for Generative Pre-trained Transformer, released in successive versions beginning in 2018. And what they found, expanding each successive version size and the amount of text it was trained on, was a set of surprisingly smooth, predictable relationships, now generally called scaling laws. Performance on the basic next word prediction task improved in a fairly reliable, continuous way as models were made larger and trained on more data, with no obvious ceiling in sight for quite a while. But something stranger accompanied that smooth improvement, and it's the detail that made this particular period of AI history feel genuinely different from anything that had come before it. As these models crossed certain thresholds of scale, they began exhibiting capabilities that nobody had explicitly trained them to have, and which weren't present, even faintly, in smaller versions of essentially the same architecture trained the same way. A model trained only to predict the next word in ordinary text turned out, past a certain scale, to be able to translate between languages it had never been explicitly taught to translate, to solve basic arithmetic problems, to follow multi-step logical instructions, to write working computer code, none of which had been the direct target of its training, and none of which its designers had specifically engineered it to do. These are generally called emergent capabilities, and their appearance wasn't gradual and predictable in the way overall next word prediction accuracy was. Often, a given capability would simply be absent, performing no better than random guessing, right up until a model crossed some particular scale, at which point performance on that specific task would rise sharply. It's worth pausing here and returning, gently, to something we set aside many chapters ago. Ada Lovelace, writing in 1843 about Babbage's unbuilt analytical engine, observed that it had no pretensions to originate anything, that it could only ever do what we knew how to order it to perform. For the better part of 2 centuries, that observation held up remarkably well against essentially every machine anyone built. Expert systems only ever did what their rules explicitly encoded. Even early neural networks, for all their capacity to learn from data rather than explicit rules, were generally trained toward one specific, narrowly defined task, and did more or less exactly that task and nothing else. Emergent capabilities in large language models complicate that old observation in a genuinely interesting way, though it's worth being careful about exactly how they complicate it. Nobody explicitly programmed rules for arithmetic or translation into these systems. Those capabilities arose, unbidden, as a byproduct of a much simpler and more general training objective, applied at a scale nobody had really tested before. Whether this counts as the machine originating something, in the sense Lovelace meant, or whether it simply means the training objective was quietly, implicitly demanding those capabilities all along, in ways too subtle for anyone to have anticipated in advance, is a question researchers are still genuinely working through, and it's one of the more fascinating open threads in the whole field right now, rather than a settled matter either way. What's a little easier to state plainly is this: the sheer scale involved in training these systems became, itself, one of the defining engineering challenges of the field's more recent history. The largest language models are trained using thousands of GPUs, running continuously for weeks or months, consuming enormous amounts of electricity and processing text at a volume that would take a single human many lifetimes to read. Later versions in the GPT lineage, and comparable models from other research groups, grew not just larger but more carefully refined in how they were trained after the initial next word prediction phase. A refinement step that connects this entire language modeling story back to a completely different thread we haven't followed in a while, one that starts, of all places, with a game of backgammon. Everything we've discussed so far involves a network learning from a fixed set of labeled examples. This image is a cat. This word should follow that one. Somebody, somewhere, already knew the right answer, and the network's whole job was to get closer and closer to matching it. But there's a different, older way a system can learn, one much closer to how a person actually picks up a new skill, and it doesn't require anyone to already know the right answer in advance. You learn to ride a bicycle not by being shown a labeled dataset of correct handlebar angles, but by wobbling, falling, adjusting, and gradually discovering, through the consequences of your own actions, which adjustments tend to keep you upright. This approach is called reinforcement learning, and its mathematical foundations trace back to work by Richard Bellman in the 1950s on how to make a whole sequence of decisions, each one affecting which options remain available later, in a way that maximizes some long-run measure of success rather than just the immediate next step. It's worth pausing on why this is a genuinely different kind of problem than anything we've discussed so far tonight. In ordinary supervised learning, the network gets told, immediately, exactly how wrong it was on every single example. In reinforcement learning, the feedback is often delayed, and worse, it's ambiguous about which of your past decisions actually deserves the credit or the blame. If you play 40 moves of a board game and then lose, which of those 40 moves was the mistake? Maybe several of them were fine, and only one made early on quietly doomed everything that followed. Figuring out how to distribute credit and blame across a whole sequence of decisions, based only on how the sequence eventually turned out, is its own substantial mathematical puzzle, sometimes called the credit assignment problem. And if that phrase sounds familiar, it should. It's a cousin of exactly the puzzle backpropagation solves within a single network, just stretched out now across time instead of across layers. Remember Arthur Samuel's checkers program from much earlier in this story, quietly improving by playing games against itself and adjusting its evaluations based on which positions tended to lead to wins rather than losses. That was an early, hand-built glimpse of exactly this idea, built on 1950s hardware with nothing resembling a formal theory behind it, mostly through Samuel's own careful intuition about how to shape the learning signal. A much more capable and more rigorously grounded descendant, called T.D. Gammon, was built by a researcher named Gerald Tesoro at IBM in the early 1990s. T.D. Gammon played backgammon against itself, millions of games in a row, using a neural network to estimate how favorable a given board position was for the player about to move, and adjusting that network, move by move, using a reinforcement learning technique called temporal difference learning, a method that lets the network learn from the gap between what it predicted a position was worth and what a slightly later position, and the network's own updated judgment of it, suggested it was actually worth. T.D. Gammon eventually reached a level competitive with the strongest human backgammon players in the world. And interestingly, it started favoring certain opening strategies that professional players had generally avoided, strategies that were later re-examined by the human backgammon community, and, in several cases, adopted, because it turned out the machine had quietly stumbled onto something correct that decades of human tournament play had overlooked. This general approach, an agent taking actions in some environment, receiving a signal about how good or bad the outcome was, and adjusting its behavior over time to seek better outcomes, reached its most publicly striking demonstration in March of 2016, in Seoul, when a system called AlphaGo, built by the DeepMind team in London, played a 5-game match against Lee Sedol, one of the strongest professional Go players of his generation. Go had long been considered a particularly stubborn holdout for computers, in a way that's worth explaining a little. because the reason is genuinely instructive, rather than just a matter of the game being generally difficult. Chess has roughly 35 reasonable moves available at a typical turn. Go, played on a much larger board with far fewer restrictions on where a piece, or rather a stone, can be placed, has closer to 250. That difference sounds modest until you consider how it compounds across a full game. The total number of possible Go games vastly exceeds the number of atoms in the observable universe, which makes the kind of brute force search that had powered chess-playing programs since the 1990s essentially useless on its own. AlphaGo's approach combined deep neural networks, trained partly on a large library of human professional games, and partly through self-play reinforcement learning very much in the spirit of TD Gammon, with a guided search process that used those networks to intelligently narrow down which of the many possible next moves were even worth spending computational effort considering. It's a lovely, much more sophisticated echo of that same old idea we first encountered all the way back at Bletchley Park, with the bomb narrowing down impossible enigma settings. Using a machine to explore a search space too vast for a human to explore directly, and using learned judgment rather than exhaustive enumeration to make that exploration tractable. AlphaGo won the match 4-1. Lee Sedol's single win in the fourth game came after he played a move so unexpected that AlphaGo's own evaluation of the position dropped sharply, and commentators at the time described it with what in retrospect looks like real relief, as proof that human creativity still had a role to play at the board. A successor system, AlphaZero, went a step further the following year, and the way it went further is worth lingering on for a moment, because it's a small but genuinely elegant idea. Rather than training on any library of human games at all, AlphaZero started from nothing but the rules of the game itself. No historical strategies, no professional games to imitate, nothing but the ability to play legal moves and to know, at the end, who had won. It then played against itself. From that blank starting point, millions of times, gradually bootstrapping its own understanding of what a good move even looked like, entirely from the consequences of its own earlier decisions. Within about 4 hours of self-play, applied to chess, it had reached a level that decisively defeated the strongest existing chess engine of the time. An engine built on decades of hand-tuned chess knowledge painstakingly encoded by human experts and programmers. It's hard not to hear an echo here of Feigenbaum's old knowledge is power hypothesis from the expert systems era, and of Rosenblatt's competing bet that learning from data and experience might get you further than hand-encoded expertise ever could. Neither bet turned out to be simply right or simply wrong, but in this particular contest, at least, the system that learned everything from scratch through its own experience outperformed the system built from decades of carefully hand-transcribed human wisdom, and it did so within an afternoon. Reinforcement learning's most significant recent contribution, though, has been considerably quieter and less publicly dramatic than a 5-game match watched by millions. And it's the thread that ties directly back to the large language models we were discussing just a chapter ago. A model trained purely to predict the next word in ordinary internet text will readily produce text that's fluent and grammatically confident, but not necessarily helpful, or honest, or safe in the way you'd want a genuine assistant to be. Which makes sense when you remember that a great deal of the text such a model learned from is itself none of those things. Internet text contains excellent writing and terrible writing, careful reasoning and confident nonsense, kindness and cruelty, all mixed together without labels attached telling the model which is which. To narrow that raw, undifferentiated fluency into something closer to a considerate, reliable conversational partner, researchers developed a technique called reinforcement learning from human feedback, generally shortened to RLHF. Human reviewers are shown several different candidate responses the model could give to the same prompt, and asked, simply, which one they prefer. Those preferences, gathered across a large number of comparisons, are used to train a separate model that learns to predict, automatically, which kinds of responses a human reviewer would tend to favor, and that prediction, in turn, becomes the reward signal used to further train the original language model through reinforcement learning, nudging it, gradually, toward producing the kinds of responses people actually judge to be good ones. It's worth sitting with this for a moment, because it means something worth noticing. The step that turns a raw next-word predictor into something that feels, in conversation, like a considerate assistant, isn't really a matter of the model suddenly acquiring new knowledge. Most of what it knows, it already learned during the earlier, much larger phase of simply predicting text. RLHF is closer to teaching an already knowledgeable system, which of its many possible ways of responding tend to actually be useful and appropriate. The way a talented but very inexperienced new employee might already know a great deal, technically, and still need real guidance on which of the many technically correct things they could say are actually the right thing to say, in this particular moment, to this particular person. And it's worth remembering, here, two things we set aside a good while ago. Weizenbaum's uneasy discovery, watching his own secretary confide in Eliza, that people readily extend real trust and real emotional weight to systems that are, underneath, following comparatively simple rules, and Turing's original imitation game, proposed as a thought experiment in 1950 precisely because he suspected the deeper philosophical question of what a machine truly understands might never be settled at all. RLHF-tuned conversational models are, in a very real sense, the first systems in this entire long history to make Turing's old proposal something people engage with casually, every day, by the millions, rather than as a formal, occasional experiment run under laboratory conditions. Whether that's cause for comfort or for a bit of healthy caution probably depends, more than anything, on how carefully we remember what Weizenbaum learned, and how honestly we hold on to it. One more thread deserves a brief mention before we bring this story to a close, and it involves images rather than words. Diffusion models, which power much of today's AI-generated imagery, work through a process that sounds almost backward at first. During training, the system takes real images and gradually adds random noise to them, step by step, until nothing recognizable remains, and it learns at each step to predict and remove a little of that noise. Once trained, the model can start from pure random noise and run that same denoising process in reverse, gradually sculpting structure out of static until a coherent image emerges guided, in modern systems, by a text description whose meaning the model has learned to associate with visual patterns during training. Drawing on the same basic idea of learned representations we've followed since the very first hidden layers back in Chapter 8, and running underneath, essentially, all of this recent progress is a genuine, actively unresolved question, one that researchers across the field are taking increasingly seriously. As these models grow larger and their internal behavior grows more capable, understanding exactly why they produce the specific outputs they do has become correspondingly harder. A field called interpretability has emerged specifically to address this, attempting to open up trained networks and trace, concretely, which internal computations are actually responsible for a given output. In something like the spirit of the emergent feature detectors we noticed inside early convolutional networks, but applied now to systems many orders of magnitude larger and more complex. It's careful, patient, unglamorous work, and it matters for reasons that go well beyond curiosity. since building systems that are genuinely trustworthy depends, in part, on being able to say something reliable about why they behave the way they do, rather than simply observing that they usually behave well and hoping that holds. Number closing. Let's go back for a moment to that duck. Nobody watching Vaucanson's mechanical bird eat and digest its grain in 1739 believed they were witnessing life. They understood, more or less, that they were looking at brass and clockwork, arranged with extraordinary patience into a sequence that merely resembled a living process. And yet something about watching that resemblance unfold closely enough was genuinely difficult to shake off. The gap between this is obviously just mechanism, and this is doing something I don't fully know how to explain, turned out to be a much narrower gap than anyone at the time expected it to stay. Everything we've walked through tonight has, in its own way, been the story of that gap slowly narrowing, and occasionally, briefly, widening again. Jacquard's loom showed that a fixed physical process could be redirected, entirely, just by changing the pattern of holes fed into it instructions, standing in for a task that had once required a person's ongoing attention. Babbage and Lovelace glimpsed, decades before anyone could build it, that the same idea might extend past arithmetic into anything expressible as symbols and rules. And Lovelace, characteristically careful, added the caveat that such a machine could only ever do what it was told. Turing gave that whole idea a rigorous mathematical foundation, and then, with the imitation game, quietly set aside the unanswerable question of what a machine truly is in favor of the answerable question of how it behaves. And then, for a long while, the field oscillated between bursts of real progress and long, discouraging winters, each time rediscovering, in one form or another, that narrow, brittle successes on carefully chosen problems don't automatically generalize into anything broader. A lesson the logic theorist ran into, an SHRDLU ran into, and the expert systems of the 1980s ran into, each in its own particular way. What finally broke that pattern wasn't a single brilliant insight arriving out of nowhere. It was old mathematics, the chain rule, sitting quietly available since the 18th century, finally applied correctly to the specific problem of assigning blame across many layers of a network at once. It was a biological observation about cat neurons, decades old, becoming the architectural blueprint for a network that could see. It was an enormous, patient effort to label millions of ordinary photographs, paired with computer chips that happened to have been built for rendering video games. Almost nothing in this story was invented from nothing. Nearly all of it was old ideas, waiting, sometimes for decades, until the right combination of data, hardware, and attention finally let them work the way their original discoverers had, in some cases, already suspected they might. And there's a specific shape to how these systems actually learn that's worth carrying with you as you drift off, because it's been the quiet undercurrent beneath everything else in this story. A neural network doesn't arrive at competence through a flash of insight. It arrives there through an enormous number of very small corrections, each one nudging a great many internal weights just slightly, in whatever direction reduces error a little further, repeated so many times that the accumulated effect eventually looks, from a distance, indistinguishable from understanding. It's the same shape Archimedes was working with when he filled the gaps beneath a parabola with smaller and smaller triangles, chasing an exact answer by approaching it, endlessly, without ever quite arriving. It's the same shape a chain of factory workers traces backward when they're trying to find out which station, far down the line, first let a small error in. Get close enough, in enough tiny steps, and the difference between approximating something and understanding it starts to become difficult to locate precisely. Which is, if you think about it for a moment, roughly the same difficulty those 18th century observers had, standing in front of a brass duck, unable to quite say where the mechanism ended and the resemblance to something alive began. We don't know yet how this particular chapter of the story ends, or even whether ends is the right word for a story that has, so far, only ever paused between one long, quiet stretch of unglamorous progress and the next. What we do know is that it's been, from the very start, a story about approach rather than arrival, about getting close enough to something, through enough small, honest steps, that the approaching and the arriving become very hard to tell apart. That's where we'll leave it for tonight.